In this section of chapter 6, I will discuss about electron configuration. Now, we already talked about different orbitals in a subshell belonging to a principal level. Now we are going to show you how many electrons are there in a particular element and in which subshell and orbitals they are present. First, I'm going to show you different orbitals and the shapes. S orbitals, they're spherical. So 1s is the smallest one, closest to the nucleus, then 2s, then 3s. So size gets bigger as n value is increased from 1 to 3. In this figure, that's what you're looking at. P orbitals, now they have two lobes, each p orbital has, and these are px, py, and pz. Remember, p orbitals belong to p subshell. P subshell has L value equals to 1, and that has 2 times L plus 1 orbitals, which is 3 orbitals. And these are the 3 orbitals. On the left hand side, you're just looking at pz orbital in electron cloud picture. Now there are 5 d orbitals because d subshell has L equals to 2. So when you have L equals to 2, there should be 5 orbitals. 2 times 2 plus 1. I hope you remember that. So it should have 5 orbitals, and these are those 5 orbitals. Now their shapes are different depending upon ml values, and each ml represents 1 orbital. To dyz, you have these lobes. Lobes are nothing but where electrons can be found. So dyz having lobes in between y and z axis. Xz has lobes between x and z axis. Similarly, xy has lobes between x and y axis. X square minus y square. Here those lobes are along x and y axis. Whereas dz square is a little bit different looking. They have like a donut type of structure, electron structure in the middle, and then you have a lobe along z axis. Now for one electron atom, could be just hydrogen, or it could be helium plus or lithium 2 plus. These are all 1 electron atoms or ions. In these cases, electron level energy sequence would be the simplest. So like n equals to 1 would have, of course, 1s subshell as well as 1s orbital, and n equals to 2 has 2s and 2p, and they have the same energy at the same level. N equals to 3 would have 3 subshells. Remember, 1 has 1 subshell, 2 has 2, 3 has 3, and those 3 would be L0, 1, and 2. So S, P, and D. Again, for 1 electron atom, 3s, 3p, and 3d would have same energy. Similarly, 4s, 4p, 4d, and 4f would have the same energy. Now, degenerate energy means they have the same energy. That's what degenerate orbitals mean. However, as the number of electrons increases, so when you increase number of electrons, even from hydrogen, if you go to helium, helium has 2 electrons. Lithium has 3 electrons. So number of electrons increased, and because of the shielding effect, which I'm going to explain in next slide, because of the shielding effect, those levels which are degenerate or having the same energy for 1 electron atom is no longer going to have the same energy. For example, for 1 electron atom like hydrogen, 2s and 2p had the same energy. 3s, 3p, and 3d had the same energy. But for many electron atoms, these levels are all different in energy, like 2s at lower energy than 2p, 3s at a lower energy than 3p or 3d. Now in next slide, I'm going to discuss what is shielding effect. In this slide, I'm showing you shielding effect or screening effect in case of many electron atoms. If you think about central nucleus like this, with a positive charge and electrons moving outside. Now let's assume that I have two electrons in the orbit that's closest to the nucleus, and then I have an electron sitting outside of that in the outer orbital. Now keep in mind, these electrons are not stationary, they're moving very fast. Now, so it would appear to the outer electron, which is I'm showing you with another green arrow, the outer electron would see only part of the positive charge because of the inner lying electrons would be covering much of the positive charge. Just like on a cloudy day, if there's a cloud in between you and the sun, then you're not going to see the sunlight. So much of the sunlight would be covered by the cloud. So it should be like a screening effect or shielding effect. In this case, S represents the screening effect, and Z is atomic number or number of protons in the nucleus. So electrons in outer orbitals would be seeing a reduced amount of positive charge, and that's why attractive force towards nucleus is going to be decreased because of the screening effect. And that's why 2s and 2p orbitals would no longer have same energy. 3s, 3p, 3d, which had same energy for one electron atom, will not have same energy. Now we are going to discuss spin quantum number, which is represented by ms value. Now this was discovered in 1920, that when there are two electrons in the same orbital, they do not have exactly the same energy, because electrons don't spin in the same manner. If one spins in clockwise direction, the other one would be spinning in anti-clockwise direction. So one gets the label of ms plus 1/2. The other electron in the same orbital would have minus 1/2. That means if one is spinning in clockwise direction, the other one would be spinning in anti-clockwise direction. Now because of this spin, they also create their magnetic field. So when you pass this kind of beam of atom with electron spin, then it would split depending upon direction of spin. And actually that's how scientists discovered that there are two types of spin, even there is one single electron. So one would be clockwise, the other would be anti-clockwise. One would get the value of plus half, the other would have the value of minus 1/2. Now here you see even better picture, and they're even showing you that how this spinning electron would give magnetic field, and it acts like a magnet with north pole and south pole. So if it is spinning in one direction, you have north pole up, outward, and south pole downward. If it's spinning the opposite way, you have south pole upward and north pole downward. That's like a magnet, any magnet, just they're flipped in different directions. Pauli exclusion principle tells us that no two electrons in the same atom can have exactly the same energy. And no two electrons in the same atom can have identical set of 4 quantum numbers, n, l, ml, and ms. So in the same orbital, if you put like 3 electrons, for example 2 electrons, they would have n, l, ml value the same, then these 2 electrons must have different ms values. One will have to have plus half, the other one will have to have minus half. And that's Pauli exclusion principle. Now here again we're talking about Pauli exclusion principle, and we're trying to apply it for one orbital and trying to put 3 electrons. So when I have one orbital, which is 1s means I have n equals to 1, and s means l equals to 0. Also, S subshell has one orbital, which is ml equals to 0. So NLML represents a particular orbital. In this case, 100 represents 1s orbital. Now let's try to put 3 electrons, forgetting about all the rules. Now look at the first one. Since it's the same orbital, I must have N, L, and ML values, exactly 100. So the first electron I put plus 1/2, second one plus 1/2, third one with a different spin, minus 1/2. Question is, would that be possible? According to Pauli exclusion principle, no, these are not possible because first two have identical set of numbers. So Pauli exclusion principle says that no two electron in an atom can have identical set of numbers like N, L, ML, and MS values. So if you can keep one of those two numbers, so let's scratch out this one, then it will be okay. So what that means is you can maximum have 2 electrons in an orbital, and when there are 2 electrons, they must have opposite spin. One having plus half, the other one would have minus half MS value. In other words, one would have clockwise spin, the other one would have anti-clockwise spin. I used to remember Pauli exclusion principle by considering that no two person in this country can have same social security number. So N, L, ML, and MS are like social security number. It's a very unique number in an atom. One electron can have a unique value of these 4 numbers. No other electron can have that. Now here we are going to apply what is called Hund's rule. If you have a same energy orbital, then electrons would fill them singly before they start pairing up. Let's focus on boron having 5 electrons. You can see the first box indicates 1s, then the second box 2s, and then 2p has 3 boxes because it's 2p subshell has L equals to 1. So L equals to 1 means 2L plus 1, that's 3 orbitals, and that's why there are 3 boxes for 2p. And boron has 5 electrons, so the 5th one goes in one of these orbitals that belongs to 2p subshell. Now if you look at nitrogen, which is this one, 1s2, first 2 goes in 1s, next 2 goes in 2s, because as I mentioned already, that any orbital you can maximum have 2 electrons, and when you have 2 electrons they must have opposite spin, and those spins are shown with up arrow and down arrow. Now we have assigned 4 in first 2 orbitals, then 2p would have 3 electrons, and here we apply Hund's rule, which says that those electrons would go and fill them singly before they start pairing up. So what that means is nitrogen has these 3 unpaired electrons, and said 1s2, 2s2, 2p3. Now it starts pairing up from oxygen, fluorine, and when you get to neon, they're all paired up. So keep this in mind. Now here I'm going to show you how you can draw electron configuration just by looking at periodic table. This is going to save your time, and so you'd be able to get these electron configurations very quickly. Let me first explain to you how this works. Say I want to get electron configuration of helium. You can see the way I wrote down on this periodic table. I have different lines on the left hand side, 1, 2, 3, 4, 5, 6, 7. This is the lines I'm referring to. Now, if you go horizontally, I wrote down S1, S2 in first 2 columns, and P1, P2, P3, P4, P5, and P6 on the rightmost columns. For electron configuration purposes, move helium from the far right, from here to here, just for electron configuration purposes. Now in middle part, where we have transition elements, I have D1, D2, D3, D4, all the way to D10. Now we are going to use the periodic table and see whether we can write down electron configuration. For helium, you're on line 1, it starts with 1. 1s1 is hydrogen, you can see that. 1s2 is helium, because I reach helium at 1s2. Let's try carbon. Now carbon is here in the second line, but as if you're reading a book, you'll have to first read line 1 before you go to line 2. Line 1 has only two things, 1s2, and once you fill in a subshell like S, P, make sure you write down that before you move to the next subshell. So it'll be 1s2, I'm done with line 1, then come to the line 2. 2s2, that gives beryllium, so I'll have to go further. Go to the rightmost, then 2p2. So electron configuration be 1s2, 2s2, 2p2 for carbon. Similarly for nitrogen it would be 2p3. So that is how it goes. Now let me show you one example of transition element. Let's pick titanium. Again, I'm reading the book starting from line 1. 1s2, I'm done with line 1. 2s2, 2p6, I'm done with line 2. 3s2, 3p6, I'm done with line 3. And then I'm at line 4 where you have titanium. 4s2, and then it's not going to be 4d. The rule is when you get to the transition elements, it will be line number -1. I wrote down in the periodic table. I don't know whether you see it clearly or not. So line number is 4, so it should be 3d2. It belongs to 3d2. I'm showing you this, 3d2. Okay? Or in a shortcut, you can write down in terms of argon configuration. This is argon configuration, followed by 4s2, 3d2. I mean, that's what we're showing you here. So make sure you understand that. And I can now go over problem number 71D, but with the help of periodic table. And of course, in exam, you can always have periodic table in front of you. Now in 71D, they gave you this. Let me write down this. Krypton configuration. Whenever you have something like this, that means you have the whole electron configuration. Krypton followed by 5s2, 4d10, 4d10, and then 5p4. Now you need to identify the element that and also the number of unpaired electrons. Now in order to identify the element, first focus on krypton. You can see the krypton is 36, element 36 is krypton, and followed by 5s2, line 5. So I'm in here in line 5, 5s2, and then you have line number -1, that's 4d10, all the way to the end of that D series. This is D10. So 4d10 and then 5p, 1, 2, 3, 4. That gives tellurium. I hope you can see it. If you look at the top of it, you see the p4, and this belongs to line 5. So this is tellurium. Now how do I find out number of unpaired electrons? The bottom ones are all filled. S is one orbital, so it can only have 2 electrons. D, L value 2, so it has 5 orbitals, and it can have 10 electrons, and it does have all 10 electrons, so all paired up. P subshell, L equals to 1, that means it has 3 orbitals, and that can have maximum of 6 electrons, but I have 4. That means I may have this question of paired or unpaired electrons with P. So let's write down 5p. I would have 3 boxes because P has 3 orbitals. P subshell has 3 orbitals. Now I have 4 electrons. I'm going to apply Hund's rule. Out of 4, first 3 electrons would go singly. Let's use a different color so that you can better see it. 1, 2, 3. First 3 would go singly, and then they would start pairing up. The first one gets paired up. So answer to this question is 2 unpaired electrons. 2 unpaired electrons. So that's the answer to 71D. Now we're going to do 74A, and then if we have a space, we'll do 74B. Now here, electron configuration represents excited states. So identify the element and write down the ground state electron configuration. So let's first write down 74A, which is 1s2, 1s2, 2s2, 3p2, and 4p1. Now, best way to find out the ground state would be first count electrons, total number of electrons. Now, total number of electrons in this case would be 7. So let's write down here 7 electrons. Now you place those electrons, and we know that 1s would be coming first, followed by 2s, and then 2p. So 1s2, 2s2, p can have total 6 electrons because there are 3 orbitals. So I don't have that many electrons, so I need only space for 3 electrons. So that makes 7 electrons. 1s2, 2s2, 2p3. Now let's find out what element is this. 1s2, you're done with line 1. Then 2s2, you're on line 2. This is line 2. 2s2, 2p3. 2p3 is on this one. So the element is nitrogen. And the ground state is 1s2, 2s2, 2p3. Ground state means normally what you'd expect. And that's basically, all these electron configuration you get from periodic table, by looking at periodic table, are ground state configurations. Now let's now try B. This is A. What we did is A. Now we're going to do B. Argon configuration followed by 3d10, 4s1, 4p4, 4p4, again I'm running out of space, 5s1. How do I get this? Now, of course, you have argon configuration, which is already filled in. I don't need to worry about that. Count electrons outside of the argon configuration. And that's altogether 16 electrons. So you have to assign 16 electrons beyond argon. So now, by looking at periodic table, you can write down electron configuration, argon. Then you'd have 4s2. Remember, look at periodic table. After argon, you have line 4, so 4s2. Then you are coming to the middle section. That would have 3d10. Still, I don't have 16 yet. I have assigned altogether 12. Then you have 4p, the far right. Now I already assigned 12. Now I need to put 4 more. And that's the ground state electron configuration. Again, look at periodic table, 4p4, the fourth line, p4 would be 1, 2, 3, 4. That's selenium. Let me circle that. So this element is selenium. Now here we're going to explain problem 71C. This is some kind of anomaly that you probably would not be able to understand just by looking at periodic table. But by following the rule that half-filled subshells are more stable than expected. So in this case, we're dealing with D5. So electron configuration is given here as 4s1, 3d5. And you're supposed to identify the element. Now, why this is stable, why you can even expect this kind of electron configuration? Because you have degenerate 3D orbitals. There are 5 orbitals there. So, and they're all thinly filled. Let me show you this. 1, 2, 3, 4, 5. And you have 5 electrons there. And in addition, there is a 4s. The 4s. They're all, I'm just going to show you. 4s has 1 electron. And 3D has 5 electrons. So these kind of electron configuration give extra stability. Now what element is this? In order to apply what we discussed by looking at periodic table, let's assume that it's not an exception. So you have 6 electrons beyond argon. So now look at periodic table. 4s2, that's line 4, you're done, you're on the line 2, line 4, 4s2, and then you're in the third, then you go into the middle section, that'd be line number -1, so that 3D, then 1, 2, 3, 4. That gives chromium. So this element is chromium, and this is an exception.